Yes. Good evening to everybody. Good evening. Yeah. So welcome to the session. Welcome to the today's class. Yeah. Yes, people are still joining. Yeah. So in the last class, we are completed that the voltage regulation methods. No? All voltage regulation methods. That is synchronous impedance method, EMMF method, ASA method, right? But among all the methods, the EMF method will give the voltage regulation more than the actual value, and MMF method gives the voltage regulation less than the actual value. So one is optimistic, another one is pessimistic. But the other two, that is ZPF and ASA, they will give the correct results. Okay, yeah. So in ZPF, in EMF method, we have taken all they will be EMF phasors. MMF method, MMF phasor. But whereas in ZPF method, we have used how many? So both EMF and MMF phasor. That is also type of the question. So you will give this is synchronous impedance method, ampere turns method, ZPF method, and whether the phasors are required. That is EMF phasor, MMF phasor. But for both for ZPF method, both MMFs both phasors are required. Only the difference for ASA, it is saturation effect is also considered. Drop due to saturation can also be considered. To compensate drop due to saturation, extra field current is required. Extra field current is required. So that gives the still more accurate result. Fine. Yeah. That is about voltage regulation methods. Fine. So once voltage regulation methods, only it is time consuming, and a lot more discussion will be there. Fine. But I have given the required information for you. Not necessary. Don't read any extra textbook, please. So whatever we have discussed, just to go through that. So I have given sufficient information which is required for any competitive examinations. Okay. Yeah. And also, yesterday we have started that short circuit ratio. Short circuit ratio is one of the important specification of synchronous machine, and the short circuit ratio is the ratios of the field current and its significance. And what the SCR indicates, it indicates the voltage regulation, armature reaction, stability of the machine, size, the cost. Okay, so all those are also depends on the SCR, short circuit ratio, and we have also derived that SCR is equal to 1 by ZS, saturated per unit or adjusted per unit. Okay, yeah. Now, then in this class, let us start the next topic, that is very important one. We are going to see from here onwards and direct. So the voltage regulation, all these things, they are time consuming. But from here onwards, individual topics are separate, and that to be, so they are interested one. Okay. Yeah. So let me start our topic, today's topic. The topic is two reaction theory. Two reaction theory. Two reaction theory. Two reaction theory. The two reaction theory for salient pole synchronous machine. For salient pole synchronous machine. Two reaction theory is required for salient pole synchronous machines. And this is given by Blundell. Given by Blundell. Blundell. So that's the reason it is namely called as Blundell two reaction theory. Blundell two reaction theory also. Yeah. In this, what is the necessity of this theory? First of all, why two reaction theory is required? Why it is required for salient pole synchronous machine? Why it is not necessary for cylindrical rotor synchronous machine? Okay, what is the reason why to have this two reaction theory? So that we are going to see. As we have discussed already, armature reaction. Armature reaction can be represented with the XA. Armature reaction is proportional to XA. Or XA is proportional to armature reaction? Yes. XA is proportional to armature reaction. XA is proportional to armature reaction. And armature reaction is inversely proportional to air gap length. Na? Yes, XA is proportional to armature reaction, but armature reaction is inversely proportional to air gap length. Air gap length, correct? Yes. Air gap length. If when air gap length varies, XA also will varies. Fine? Yeah. If you take in cylindrical rotor synchronous machine, air gap is uniform. In cylindrical machine, air gap is uniform. But whereas salient pole synchronous machine, air gap varies. Air gap is different along the direct axis and quadrature axis. So around the entire air gap periphery, air gap is different. Fine? Yeah. So XA is inversely proportional to air gap length. Correct? XA is inversely proportional to, in other words, from this, XA is inversely proportional to air gap length. XA is inversely proportional to air gap length. Now, first of all, let us see one by one for cylindrical machine and salient pole synchronous machine. In cylindrical rotor synchronous machine, only single reactance is sufficient, only one reactance, because everywhere air gap is same. Everywhere air gap is same. Whatever may be the power factor, so it finds same air gap. So one reactance is sufficient. But whereas in salient pole synchronous machine, air gap is non-uniform. There it requires two reactances. That is, we are going to call two reaction theory. Let us discuss in detail about. So I will compare with both cylindrical and also salient pole machine. So for better understanding purpose, let me take both. First, I will take cylindrical rotor synchronous machine. First, cylindrical rotor synchronous machine. Cylindrical rotor synchronous machine. In cylindrical rotor synchronous machine, air gap is uniform, na? Yes. This is the rotor. I have to take cylindrical rotor. Cylindrical rotor. This is a cylindrical rotor. Right? Yeah. On the cylindrical rotor, there will be windings are there, na? Yes. There are the windings. Slotted area and unslotted area. There is a slotted area and unslotted area. Of course, based on that, in this, the winding is there. Based on the current direction, cross, 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 here dot, dot, say, it is acting as a north pole and this is acting as a south pole. South pole. And we have seen rotor is rotating in counterclockwise direction. When rotor is rotating in counterclockwise direction, the induced EMF will be in this direction. This is induced EMF, E. E is along the, not induced EMF, flux. This is the flux, main field flux, phi m or Fm. So that is along the D axis, no? That is along the direct axis. But induced EMF is along the quadrature axis. Induced EMF is along the quadrature axis. This is E. E. So that E lacks the flux by 90 degrees. E lacks the flux by 90 degrees. Rotation is in counterclockwise direction. And for UPF, if you take for unity power factor, this is E, and this is also current IA, and this is also FA, and this is also armature flux. That will be along the Q axis, no? Yes, all they are along the Q axis. Q axis. Rotor is rotating in counterclockwise direction. This is for UPF, unity power factor. This is for unity power factor. Cylindrical rotor synchronous machine. Similarly, if you take for some 0.8 lagging power factor, say, some 0.8 lagging power factor, if you take, for 0.8 lagging power factor, same machine. Right? Yeah. So this is north pole and south pole. So here winding there, fine. Based on the current direction, this is acting as a north pole and south pole. North and south pole. The flux direction is in the same direction. This is main field flux is along the direct axis. Main field flux along the direct axis. But induced EMF is always along the quadrature axis. This already we have seen. I have shown at the time of how to draw the phasor. This is induced EMF. That is quadrature axis, Q axis. But if you draw for 0.8 lagging power factor, this is, I want to draw for 0.8 lagging power factor, say. This diagram is for 0.8 lagging power factor. For 0.8 lagging power factor, where IA will be, IA lags. This is IA, say. IA, it is lagging with some angle. This is IA. When this is IA means FA also in the same direction. FA also is in the same direction. Phi A also in the same direction. Fine, yes. It is a FA. Now, if you compare, this is of course power factor angle psi I am taking, psi. This is the psi, internal power factor angle psi we are taking. Right? Of course, psi is equal to phi plus delta. Now, if you, from the two diagrams, here psi is equal to 0, power factor angle is 0. Now, in two cases, what we will observe is, FA is here, na? FA is here. FA is along the quadrature axis, right? Now it is finding the same air gap. What is the air gap for MMF? Air gap for MMF is the same. And here, air gap for MMF is same. The air gap is same. It is finding same air gap. Air gap is same for unity power factor and also for 0.8 lagging power factor also. FA observe. FA find same reluctance. FA find same reluctance, same air gap for UPF and also for 0.8 lagging power factor. 0.8 lagging power factor. Okay. And for any power factor, so it finds same reluctance, same air gap means therefore it finds same reluctance. FA find same reluctance. FA find the same reluctance. Irrespective of power factor. Wherever it may be. So I have taken 0.8 lagging, but you can take for any other power factor also, it find the same reluctance. Air gap length is same, na? Yes. Air gap length is same. It finds same reluctance. So effect of armature reaction is same. Therefore, effect of armature reaction, wherever may be the position for any power factor, the air gap is same, reluctance is same. Therefore, one single reactance is sufficient. Reluctance is same, na? Reluctance is same. So single reactance is sufficient for modeling the armature reaction. Therefore, single reactance single reactance is sufficient. Is sufficient for modeling the armature reaction. For modeling the armature reaction. Only one reactance is sufficient, that is XA, because everywhere it is finding same air gap, na? Yes. And that to be, we know armature reaction is inversely proportional to air gap length. So as air gap is same, right? Armature reaction is same. Therefore, XA also same. XA one component is sufficient wherever it may be. Okay, one XA is sufficient. Since air gap is same, na? Yes. XA is inversely proportional to air gap length. XA is inversely proportional to air gap length. So air gap is same, XA also same. In for UPF also 0.8 lagging power factor also. If, but whereas for salient pole synchronous machine, let us see. For salient pole synchronous machine, let us compare for salient pole synchronous machine. For salient pole synchronous machine, for salient pole synchronous machine. For salient pole synchronous machine, again I would like to observe both for UPF and also lagging power factor. I'm taking for salient pole machine. Okay, say this is north pole and south pole. Rotor is rotating in counterclockwise direction only. Rotor is rotating in counterclockwise direction. This is the main field flux. Main field flux is in this direction. That is along the direct axis. That is along direct axis. Induced EMF is quadrature axis. Induced EMF is quadrature axis. This is E. This is fixed already. I have shown. Okay, induced EMF is along the quadrature axis. For unity power factor, if you take, for unity power factor, IA here and FA will be here. FA is same. Phi also same. This is for unity power factor for UPF. And similarly, for 0.8 lagging power factor, if you take, for 0.8 lagging power factor, for 0.8 lagging power factor, north pole, south pole. This is main field flux. Phi m is along D axis. Induced EMF is along the Q axis. E. Let us take for 0.8 lagging power factor. If you take for 0.8 lagging power factor, is IA. Then FA. This is going to be FA. This is the psi. Of course, power factor angle is equal to phi angle between V and IA. To identify armature reaction, I am taking internal power factor angle, E and IA. Yeah. Now, you observe here the main difference between for 0.8 lagging power factor, see, FA, you take reference as FA. FA is finding this much air gap length. Here for unity power factor. But what is the air gap length for this? Air gap length is less. Here air gap length is less for FA, for 0.8 lagging power factor. The FA offer less reluctance for 0.8 lagging power factor, more for unity power factor. Like that, as power factor changes, as phi changes, psi also changes. As psi changes means FA will find different the air gaps. For example, of course, I am going to draw. I'm going to rub this, but you observe. So for example, I want to take here. I want to take here for this power factor. Say for this power factor, what is the air gap length? You see here, air gap is reduced. Less air gap. FA will be here. No, air gap is less. When air gap is less means is the armature reaction is same? Armature reaction is not same. And we know that XA, armature reaction is proportional to XA. XA is proportional to armature reaction, but armature reaction is inversely proportional to air gap length. Armature reaction is proportional to air gap length. But what happened? The FA is finding different air gaps. UPF air gap is different. Na? Unity power factor air gap is more. FA finding. But here 0.8 lagging, it is finding different air gap. Whereas for 0.707 lagging, say, as phi increases, it is still finding less reactance. Less reluctance. So armature reaction is different. When for FA is there, different instants, armature reaction is different. So XA also must be different. Na? Yes. So single reactance is not sufficient. And that to be, we cannot take at the same time so many reactances also. So many reactances also. As power factor changes, FA offers various reluctance, different reluctance. But which XA you can take? Is single reactance is sufficient or no? It won't sufficient. But whereas cylindrical emission we have observed, na? Cylindrical emission everywhere air gap is same. Everywhere air gap is same for any power factor. Reactance one sufficient. But here the problem is, so as psi changes, FA find different reluctance. Different reluctance. This problem can be resolved. Then how you can model the armature reaction? As air gap changes, how you can model the armature reaction? This problem can be resolved. That is given by Blundell. What he has proposed, that the bundle is proposed. Instead of having FA, let us divide that FA into two components. FA can be divided into two components. One along the direct axis, another along the quadrature axis. This is one FA. It is divided along the two components. This is FAD, direct axis component, and this is the quadrature axis component, FAQ. Direct axis and this is quadrature axis. Yes. Now you can observe any component, whatever it may be. Along the direct axis, air gap is minimum, and quadrature axis air gap is maximum. Quadrature axis air gap is maximum. Direct axis air gap is minimum. So irrespective of power factor, so we can divide that into two components, means FAD, FAQ. So always FAD will find minimum reluctance, FAQ find maximum reluctance. Any power factor, reluctance now becomes along the direct axis same, constant, minimum and maximum, both are fixed. So two reactances are sufficient. This problem can be resolved by taking instead of taking only single reactance, two reactances, one along the direct axis, another along the quadrature axis. So I can take here one reactance is FAD is there, na? Yes. XEAD we will take one reactance, XEAD. And this side it is XEAQ. Two reactances we will take. This problem can be solved by taking the two reactances instead of single reactance. There only one reactant sufficient. Two reactants are required. Now can you tell me here air gap is length along the direct axis, air gap length. When air gap is minimum, now here air gap is minimum. When air gap is minimum along D axis, then what is the armature reaction? Air gap is minimum. Therefore, armature reaction is maximum along D axis. Armature reaction is maximum. Then XEAD. Then XEAD will be greater than the XEAQ, na? Yes, armature reaction is maximum. But what about along the quadrature axis? Along the quadrature axis, air gap is minimum. Air gap is minimum. Therefore, armature reaction is maximum. Armature reaction is maximum. Sorry, air gap is maximum. Armature reaction is minimum. air gap is maximum, therefore armature reaction is minimum. So that can be taken with XEAQ. Can you tell me which is greater? XEAD will be greater than the XEAQ. XEAD will be greater than XEAQ because armature reaction is more along the direct axis. Armature reaction is more along the direct axis. So this problem can be resolved with 2 reactants are sufficient. Instead of taking for every power factor different reactances, any power factor 2 reactants are sufficient. They are constant, XED constant. Why? Because their air gap is same. Okay. Yeah, these are said to be 2 reactances theory. 2 reactances theory because armature reaction is different along direct axis and quadrature axis. Okay. Yeah. Now see, let me write these things. In cylindrical rotor synchronous machine, 1 reactant sufficient, but whereas salient pole synchronous machine, 2 reactants are required. In salient pole synchronous machine, the FEA will find different reluctances and different air gaps for various power factors. As phi changes, psi also changes. Therefore, FEA offer reluctance for FEA will change. Reluctance for FEA will change. Therefore, armature reaction will be different. The armature reaction, single reactance is not sufficient for this. And the FEA will change means single reactance is not sufficient. Therefore, single reactance is not sufficient. Single reactance is not sufficient for modeling the armature reaction. Is not sufficient for modeling the armature reaction. Okay, but it requires 2 reactances. Not sufficient for single reactance modeling for armature reaction. Therefore, this problem can be resolved. By dividing FEA into 2 components. That is, one along the direct axis, one along D axis, that is FEAD, another along quadrature axis. Another along quadrature axis, that is FEAQ. So therefore, armature reaction can be modeled with, armature reaction. But FEA and FEAD, so of course, FEAD always find minimum reluctance, and FEAQ always find a maximum reluctance, irrespective of power factor. So therefore, there becomes constant now. FEAD, FEAQ, they becomes reluctances are constant. When reluctance constant, air gap constant means the reactance is also constant. Therefore, the armature reaction can be modeled. Armature reaction can be modeled with XCAD along direct axis, XCAD along D axis, and XCAQ along Q axis. XCAQ along Q axis. Therefore, two reactances are required. Two reactants are required for modeling the armature reaction. So two reactances are required. Right? Two reactances are required. Two reactances, XCAD and XCAQ, are required for modeling the armature reaction. For modeling the armature reaction. Okay. Therefore, called two reactances theory. Two reaction theory. The FA is divided among two, na? Yes, two reaction theory. Two reaction theory. That is FEAD and FAQ. What is FEAD? MMF, armature MMF, na? Armature MMF. Or two reactances theory. Two reactances theory. XCAD and XCAQ. Two reactances theory. Fine? Yeah. But whereas in cylindrical, XCAD, XCAQ both are same. XCAD, XCAQ both are same. One reactant sufficient. XCAD, XCAQ is equal to XCA. That is what I am going to write. Okay? Yeah. But whereas reluctance is same. Leakage reactance is same. XCAD difference, but leakage reactance. What taken this now? Fine. Leakage reactance. XL is same along the direct axis and quadrature axis. XL is same only. XL will be taken same. Here also XL will be same. XL will be same. So then what is the total reactance? XL is same both along the direct axis and also quadrature axis. Let me write here. XL, leakage reactance. XL can be taken same along the direct axis, same along the D axis and Q axis. Therefore, what is the total reactance along D axis? Along D axis, total reactance, that is XCAD plus XCL. XCAD plus XCL, that is called XD. Total reactance along the direct axis. Total reactance along the direct axis is XCAD plus XCL. That is called what? XD. This is called synchronous reactance. Direct axis synchronous reactance. XCAD is called armature reaction reactance along the direct axis. XD is called direct axis synchronous reactance. But what is XCAD? XCAD is called direct axis armature reaction reactance. That is said to be direct axis armature reaction reactance. XCAD is said. XD is direct axis armature reaction reactance. And similarly, along the quadrature axis also. Along the quadrature axis. Along Q axis, if you take total reactance is XCAQ plus XCL. That is equal to what? XQ. It is said to be quadrature axis synchronous reactance. Fine. The quadrature axis synchronous reactance, XQ. But what is XEAD? XEAD is called direct axis. XEAD is called direct axis armature reaction reactance. Direct axis armature reaction reactance. Armature reaction reactance. XEAQ is called quadrature axis armature reaction reactance. Quadrature axis armature reaction reactance. Quadrature axis, are you getting? Synchronous means what? XEA only, XEAD I am writing. XEA suffix D, XEA suffix Q. Instead of simply saying XEA, XEAD I am calling XEAQ. Okay. But XEA plus XEL, that is called what? Synchronous reactance, XES. XES only I am calling XD. XD. Right? Yeah. Now which is more, tell me, is XD is greater or XEQ is greater? XD will be greater because XEAD is greater. XEAD will be greater than the XEAQ. Right? Yes. Because say XEAD, XEA is proportional to armature reaction. Armature reaction, but that is inversely proportional to air gap length. Air gap length. Therefore, air gap is minimum. Air gap is minimum along D axis. Along D axis. Therefore, armature reaction is maximum. Armature reaction is maximum. Armature reaction is maximum. But air gap is, now what is air gap is? Maximum along Q axis. Air gap is maximum along Q axis. Along Q axis. Therefore, armature reaction is minimum. Armature reaction is minimum. So, this is XEAD. XEAD, this is XEAQ. Therefore, which is greater? XEAD will be greater than the XEAQ. XEAD will be greater than XEAQ. Since armature reaction is more along direct axis, since armature reaction is maximum along D axis. So therefore, XEAD will be greater than the XEAQ. Okay, I hope with this statement you can understand. XEAD will be greater than XEAQ. Now, what about XD? Definitely XD also will be greater than XEAQ. XD, armature reaction, and XEA is proportional to armature reaction. Yes, XEA is proportional to armature reaction. That's the reason it is coming. XEA, armature reaction. So XD also, therefore XD also will be greater than the XQ. XD also will be greater than the XQ. XQ. XD generally it is 1.5 to 2 times of XQ. Dear students, XD is 1.5 to 1.2 times of XQ. But in most of the cases, it will be 1.6 times of XQ is more common. Is more common. In most of the machines, XD will be nearly 1.6 times of XQ. Most of 160% XD will be very common. Okay, yes, 160%. And this XD minus XQ, XD minus XQ is called saliency. XD minus XQ is called saliency. XD minus XQ is called saliency. So, in simple word, you can say armature reaction is different along D axis, Q axis. So, two reactants are required. Two reactants, XEAD, XEAQ. But for cylindrical rotor synchronous machine, XEAD, XEAQ both are equal. That is equal to XEA. Both are equal. Only one reactance. Either you take XEAD, that also XEAD, that is itself XEAQ. Yeah. Lastly, for cylindrical machine, for cylindrical rotor machine, air gap is same. Air gap is uniform. Air gap is uniform. Therefore, armature reaction also same. Therefore, armature reaction is same along D axis and Q axis. Same along D axis and Q axis. D axis and Q axis. D axis and Q axis. Therefore, single reactance is sufficient. Single reactance is sufficient. Single reactance is sufficient. Single reactance is sufficient. That is, XEAD is equal to XEAQ. That is equal to XEA. Both are equal. XEAD is equal to XEAQ is equal to XEA. Both are equal. Similarly, XD also equal to. Similarly, XD is equal to XEQ. That is equal to what? XES. XES. Both are same. XD, XQ in cylindrical rotor synchronous machine. This is for cylindrical rotor machine. Cylindrical rotor synchronous machine. It will be same. Okay. Then what is XD minus XQ? XD minus XQ is equal to 0. 0. That is said to be zero saliency. Zero saliency. No saliency. No saliency. That's the reason it is called non-salient pole. Do you remember? Very beginning classes I have given. Cylindrical rotor alternator also can be called as non-salient pole synchronous machine. Non-salient pole. Saliency, they are not projecting type. Na? Air gap is uniform for cylindrical machine. Air gap is same. Therefore, only one reactance, that is XD, that is equal to XQ. Both are equal. XD is equal to XQ. FEAD is equal to FAQ. Reluctance is same. FEAD magnitude may changes, but reluctance is same always. Reluctance is same. FEAD, FAQ, they will find same reluctances because air gap same. But salient pole, it is not like that. Air gap is changes, na? Okay. Now, this is called two reactances theory. So, two reactances are required for only salient pole synchronous machine, not required for cylindrical machine. Okay. Yeah. This is about two reaction theory. Okay. When reactances are different means its phasor diagram also different. Phasor diagram for salient pole synchronous machine will be different. Because we need to divide, current also will be along direct axis and quadrature axis. Reactances, once you are divided, the current also can be divided, IDIQ. IDIQ. Okay. So now let us draw the phasor diagram of salient pole synchronous machine. Phasor diagram of salient pole synchronous machine. Phasor diagram of salient pole alternator. Salient pole alternator. Phasor diagram of salient pole alternator. Yeah. So for salient pole alternator, let us see. First, I will start with the direct axis. No, yes, this is direct axis. This is phi m. Phi m is along D axis. D axis. Induced EMF is along the Q axis. Induced EMF is going to be here. That will be the induced EMF will be along the quadrature axis. Induced EMF along the quadrature. This will be decided that along the Q axis. Now what is V? V lags. V will be lags. This is V, say V lags. V lags the E with an angle delta. And current, this is the current, say IA. This is IA. lagging power factor I am drawing IA, and IA can be divided into two components. Current also can be divided into two components. Are you getting IA? V lags, na? The vertical line is E. This is going to be E. So V lags. Phasors are rotating in counterclockwise direction. Phasors are rotating in counterclockwise direction. Therefore, V lags. IA lags for lagging power factor. Now, what we want to do is IA can be divided into two components. This IA is there, na? IA can be divided into two components. One along the direct axis, another along the quadrature axis. This is ID, direct axis current, along the direct axis. This is along the direct axis. And this is quadrature axis component, IQ. Current can be divided into ID and IQ, quadrature axis component. Yeah, now, then once current is divided, now ID RA, how resistance drop? Resistance drop will be in phase with current. Reactance drop is perpendicular. That you may be knowing. Correct? Resistance drop is in phase with the current. Reactance drop is perpendicular. Therefore, let me start all the drops. All the drops should be added from V. V plus IARA. IDRA. First I will take IDRA. This is V, na? Yes. This is IDRA. Because I am drawing IDRA in phase with the IA. Am I right? ID like this. IDRA in phase. Similarly, IQ. IQ is vertical. Therefore, IQRA. This is IQRA. This is IQRA. IQRA. IQRA in phase with IQ. Then what about ID? IDXD. IDXD. That IDXD will be perpendicular to this. This is going to be IDXD. IDXD. 1 minute. Okay. IDXD. IDXD will be perpendicular to this. IDXD. Yeah, this is IDXD. IDXD is perpendicular to ID, no? Yes, this is ID. IDXD perpendicular. Now IQXQ will be again perpendicular to IQ. This is IQXQ. This is IQXQ. So finally, this is E. So this is IQXQ. IQXQ. Okay. This is IQXQ. Whereas this is IDXD. This is a phasor diagram of salient pole synchronous machine. Phasor diagram of salient pole synchronous machine. I hope this is very clear. This is E. Now V lags. V lags with an angle delta. This is going to be delta. I am taking for lagging power factor IA. Thing is, IA divided into two components, ID and IQ. One component ID, one component IQ. Now, from the tip of V vector, add all the drops. From V, I am starting. To obtain E, what to do? All the drops has to be added. See, this is IDRA. IDRA in phase with ID. And this is IQRA. IQRA is in phase with IQ. Both are in same phase. And this is ID. ID means IDXD perpendicular. IDXD perpendicular. And IQXQ also perpendicular to IQ. Is a phasor diagram of salient pole alternator. And what is this angles? See, this angle is called delta. This angle is delta. And this angle is phi. Phi is the angle between V and IA, load power factor angle. And this is psi. Psi is the angle between E and IA. E and IA. So delta. See, delta is the angle between E and V. E and V. And phi is the angle between V and IA. V and IA. Psi. Psi is the angle between E and IA. E and IA. Okay. Yeah. And what is the psi? Psi is equal to, you can find. Psi is equal to, can I write phi plus delta? Yes, 5 plus delta. For lagging power factor, it is plus. Lagging power factor, it will be plus delta. The leading power factor, if you take, psi is equal to 5 minus delta. Okay, from this is psi. Psi na angle between E and V, E and IA. So this is delta plus psi, delta plus phi, delta plus phi. So psi is equal to delta plus or minus phi. Plus for lagging power factor, minus for leading power factor. Plus is for lagging power factor, and minus UPF also you use plus always, use plus. Minus is for leading power factor. Minus is for leading power factor. That's the sign. And ID is equal to, this is sin, yes. Can you tell me what is ID? ID is equal to IA sin psi. IQ is equal to IA cos psi. This IA angle is between this and this is sin psi. Now IQ is the adjacent component, ID is the opposite component. This both are same, no? Yes. This is ID same. So I can write ID is equal to IA sin psi. That is nothing but direct axis armature current. Direct axis armature current. IQ is equal to IA cos psi. It is quadrature axis. Armature current. IQ, that is IQ. Okay, yeah. Next, another important relations, remember that, another important relation, tan psi is equal to, these are the currents, no? Currents. And another important relation is tan psi is equal to, let me write first, directly I will write, tan psi is equal to V sin phi plus or minus IA xq plus or minus IA xq divided by V cos phi plus IA RA. How it is coming, that we are going to see. I will derive this equation. I am going to derive this equation. These are the very important relations. On this, we are going to do the problems. Okay, that is. And plus is for lagging power factor. Plus is for lagging power factor and also UPF. Minus is for leading power factor. Tan psi, to find the psi value. Similarly, if you want to find E value, say E is equal to, listen here. This I am going to explain how tan psi is coming. Derivation I am going to do later at the end. But E, to find the EC, this is what E cos delta, correct? This is V cos delta. Okay, this is delta, na? This is delta. So angle between E and V, delta, V cos delta. This is IQ RA. And this is IDXD. Now can I write E is equal to, this is E, I am dividing into different components. E I am dividing that into V cos delta plus IQ RA plus IDXD. Correct? This total E is equal to V cos delta plus IQ RA plus IDXD. So therefore, let me write that E is equal to V cos delta plus IQ RA plus or minus IDXD. ID XD. With left side, because I need some space. So E is equal to V cos delta plus IQ RA plus or minus ID XD. Plus is for lagging power factor, plus for lagging power factor and UPF, minus is for leading power factor. Okay. Dear students, very, very important relations. These are, we are going to the problems on this. Very important relations. We have done so far two types of problems. One is EMF equation, one is on voltage regulation. In our alternator, total 6 type of problems, 6 type. So 2 types already completed, EMF equation problem and also voltage regulation. Now, what is the third type of problem? Third type of problem on two reaction theory. These are only the relations. Okay, here some student will raise a doubt. Sir, E is equal to simply V plus IARA plus J into IA XD XQ. You can do like that. But when J component is coming, phase angle will comes into picture. When phase angle means in the calculator, operation is different. Calculation operation becomes a bit tedious, no? Yes, virtual calculator that to be. So what we are trying to do is, we are making it is a no phase or nothing, direct magnitudes. Direct magnitudes. Here, how examination questions that will be asked, listen. I will ask from this data, delta I will ask to calculate. How can you calculate delta? Delta can be calculated by using this, tan psi. Tan psi is equal to V sin phi plus or minus IA XQ divided by V cos phi plus IARA. But tan psi, phi will give, power factor will give, XQ other things. So from this tan psi calculated. Once you are calculated tan psi, delta I can calculate from this relation. Delta can be calculated. Okay. And once psi calculated, ID I can calculate, direct axis current. Quadrature axis current I can calculate. And once delta, you know, E can be calculated. Because E is equal to V cos delta plus IQRA plus ID XD. Delta can be obtained from these relations. So that once you know the E, regulation also we can find. After this, I am going to do the problems. Right? Yeah. Okay. An important thing is, I just want to derive this equation. How tan psi, everything is same. All the information you can get from this phasor diagram. From the phasor diagram, you can remember psi is equal to phi plus delta. ID also you can remember. E also you can find. A bit practice and you can, no need to forget. Even if you forget also, with the simple diagram, you can able to recollect that. But how tan psi, so that is from derivation. Let me derive that. After that, we are going to the problems. Okay. This is taken, na? Yeah. Now, derivation, how tan psi is coming. This is phi. Phi m. Again, I am drawing the phasor diagram. This is E. Okay. So V. This is V. IA. The V, IA, okay, right? This is IA. Now, IA can be divided into two components now. Of course, same phasor diagram. Once again, I am writing, because if I draw there, already it is clumsy. So to have the clarity, I am taking another diagram. This is ID. Okay, this is IQ. Same phasor diagram. This is IA, fine. Now IDRA can be divided into IDRA, and this is IQRA. This is IQRA. And IDXD, this is IDXD. IDXD. And this is IQXQ. This is IDXD. This is IQXQ. What is this? This is E. Fine. So IQRA, this is IQRA. This is IDRA. What about this? This is IARA. This is itself IARA. Dear students, this is itself IARA. IA is in same phase with the ID. That is IARA. Now, see, this is delta. This is delta. Angle between this is delta. This is phi. That is phi. This is psi. That is psi. Okay. This is the phasor diagram, whatever I have drawn earlier also, the same thing. Now, let us divide this into two components. I can divide into two components. V can be divided into two components. V cos phi, V sin phi. Let us divide that into. This is V cos phi and V sin phi. V I am dividing again into two components. This is one component, V cos phi. Okay. Of course, this is IARA. This is IARA. Now, I am dividing this into, extend this point onto here. Extend this point to here. Extend this point to here. And again, extend like this. Fine. Okay. Yes. See, this is point O. Let me take. This is point what? O. What is this point? A, say. A. This is point B. This is point C. This is point D, say. D. This is D. This is E. You take E. This is point F. That is point F. Fine? Yeah. But what is OA? Tell me. OA is equal to V cos phi. Right? From this right angle triangle. This is right angle triangle. This is right angle triangle. This is also right angle triangle. What is that? OA is equal to V cos phi. OA is equal to V cos phi. And AD is equal to BC. AD is equal to BC is equal to V sin phi. And of course, AB is equal to DC is equal to IARA. Fine? IARA. Now what is CE? Right. From this, CF is equal to IQXQ. CF is equal to IQXQ. CF is equal to IQXQ. Right? CF is equal to IQXQ. Important thing here to observe. Normally, if you to see the textbooks, you cannot understand this derivation. But this derivation we are going to use so many times. That's the reason I am interested to derive this relation. See, dear students, stop writing. Listen. IQXQ is equal to. First of all, what is IQ? Tell me. IQXQ is equal to IQ. IQXQ is equal to. I can write IQ is equal to IA cos psi, na? IQ is equal to IA cos psi into XQ. XQ. Therefore, IQ XQ is equal to, can I write IA XQ cos psi? Yes. IQ XQ is equal to, this is the important thing is, IQ XQ is equal to IA XQ cos psi. Cos psi. See. This is important thing. IQ XQ is equal to IA XQ. I am writing IQ is equal to IA cos psi now. IA cos psi. XQ I am multiplying. Fine. Now coming to the important thing is, this is when IQ XQ is equal to, can I write it is equal to, that is itself equal to, this is equal to IQ XQ cos psi. Cos psi. This is nothing but that much. This is equal to IQ XQ cos psi. When this is IQ XQ cos psi, see the angle, dear students. See the angle. This is psi. This is psi. This is 90. What is this angle? This angle will be 90 minus psi now. Yes, this is angle is 90 minus psi. 90 minus psi. What is this angle? This is the psi. This is the psi. That is the psi. So when that is psi, from CEF, from right angle triangle CEF, say, from right angle triangle CEF, EF is equal to, EF is equal to IA XQ. That is equal to IA XQ. I am writing that is, sorry, IQ XQ. I am writing IA XQ cos psi. Cos psi. Cos psi. Therefore, CE is equal to, that is CE is equal to IA XQ. IA XQ. Because from the right angle triangle, you see, IA XQ is adjacent side. Then what is CE? Hypotenuse. C is hypotenuse. That is equal to IA XQ. Correct? Yes. Okay? Yeah. Right. Now from this, yeah. From this, from right angle triangle, see, finally from the right angle triangle OBE, I can see from the right angle triangle OBE, from right angle triangle OBE, tan psi is equal to what? Tan psi is equal to, finally this is what we have got, CE is equal to IA XQ. This is, we have got IA XQ. Okay. IA XQ. Now tan psi is equal to what? Tan psi is equal to, from the right angle triangle OBE, tan psi is equal to opposite side, BE divided by OB. BE divided by OE. But BE is equal to BC plus CE divided by OB is equal to OA plus AB. OA plus AB. But what is BC? We know BC is equal to V sin phi, na? Yes, BC is equal to V sin phi. From this diagram, you can find here BC is equal to V sin phi. BC is equal to V sin phi. What is CE? CE is equal to IA XQ. IA XQ divided by OA. OA is equal to V sin phi, V cos phi. AB is equal to IA RA. Therefore, tan psi is equal to V sin phi plus IA RA, IA XQ divided by V cos phi plus IA RA. V cos phi plus IA RA. This is whatever I have derived for lagging perfector. Okay. Okay. Yes. That's what the derivation. But you need to remember this equation. Salient pole mission also same relations. Wherever plus is there, it will be minus. Minus. I will write at the end. Okay. Yeah. Now, then let us do the problems on this. Very important problems. GATE examination particularly is asking based on this. Two reaction theory and a salient pole machine. The two reaction theory is one important episode. What is two reaction theory? What is the phasor diagram? What is the slip test? Measurement of XD, X cube. This part is one of the important episode, right? And the examiner is very much interested to ask the questions on salient pole machine. These are only the topic. So let us do the problems. Yeah. Okay. The question is like this. Okay. Any doubt on this, Ashish Raj? Tell me just 1 minute. I will attempt your doubts. Ashish Raj, tell me what is your doubt?
Hello, sir.
Tell me.
You have written that CF is equals to IQXQ. I think, sir, that is CE.
CF is not IDXD. CF is not IDXD.
IQXQ.
EF is equal to IQXQ. Oh, sorry.
Yeah,
you're right. That is EF, not CF, EF. EF is equal to IQXQ. Yes.
Yes, sir. That one.
Yeah. Correct. So it looks like C and E similar. Okay. Now let us do the problems mainly on this. Let us go to the problems. Right. Yeah. The problem is, take down the problem. I will dictate it. It won't take much time. A salient pole synchronous generator with negligible RA, with negligible resistance, has per unit values, has per unit parameters XD is equal to 0.8 per unit and XQ is equal to 0.5 per unit. If the generator is supplying, rated kVA at rated voltage. Rated kVA at rated voltage and at 0.8 lagging power factor. And yet 0.8 lagging power factor. So under that, question number 20, you can find your material. The load angle is dash. Question 21, the excitation EMF is dash. Excitation EMF is dash. Okay, similarly, regulation is dash. Let us say regulation is dash. This is a question for you. Okay. The solution is mainly is giving in per unit values. It is given per unit values. When rated kVA means 1 per unit. Rated kVA 1 per unit. So it is given rated kVA, rated voltage. Rated voltage means V is equal to 1 per unit. We have to take 1 per unit. And also rated kVA. He has given rated kVA. Therefore, IA also equal to 1 per unit we can take. Current also will be taken 1 per unit. Why? Because KVA rated. Voltage already rated. KVA rated means voltage into current. Current also will be rated. And power factor is given. Okay. Power factor is 0.8 lagging. 0.8 lagging power factor. XD given. XD is equal to 0.8 per unit. XQ 0.5 per unit. 0.5 per unit. Then first to calculate tan psi. Tan psi. You need to calculate delta. First to calculate tan psi. Tan psi is equal to tan psi. Question number 20 I am doing. Tan psi is equal to, we know that V sin phi plus lagging power factor, no? Yes, plus IA XQ divided by V cos phi plus IA RA. So what is V sin phi? V is equal to 1 per unit. Sin phi is 0.6. Cos phi 0.8 lagging. Sin phi 0.6 plus IA. IA is equal to 1. XQ, how much it is given? XQ is given 0.5. XQ is 0.5 divided by V cos phi. That is 1 into how much? V cos phi. V cos phi is equal to, that will be 0.8. V into 1 into 0.5. 0.8 plus IA. RA 0, na? Yes. So that is tan psi. From this, we can calculate psi value. From this, what is the psi value? If you calculate, psi is equal to 53.97, you will get 53.97 degrees. You can calculate and check it. Okay. But once you know the psi, and we know psi is equal to what? 5 plus delta. Psi is equal to 5 plus delta. Therefore, what is delta? Delta is equal to psi minus 5. Psi minus 5. Psi we know 53.97 degrees. Phi is equal to how much? 36.86 degrees. Correct. 36.86. Then what is the delta? It is 17.11 degrees. Therefore, answer is delta is equal to 17.11 degree. This is one answer. This is a delta. Okay. Yeah. We have calculated tan psi, delta. Next, 21. Question number 21. Question number 21 is excitation EMF. E you need to calculate. E, excitation EMF means what? E is called excitation EMF. Generated EMF or excitation EMF. Yeah. But for that, it is required ID, IQ also. ID is equal to what? IA sin psi. ID is equal to IA sin psi. That is 1 into sin psi is sin psi 53.97. Psi is equal to 53.97. Na? Yes. That is equal to how much? 0.808 per unit. 0.808 per unit. Similarly, IQ. IQ is equal to IA cos psi. That is 1 into cos 53.97. 53.97. That is equal to 0.588. 0.588 per unit. Okay. Then excitation EMF E. Excitation EMF. That is nothing but E. E is equal to, we know that already. V cos delta plus IQ RA plus ID into XD. ID into XD. So V 1 per unit. Cos delta how much? 17.11 plus IQ. IQ is equal to 0.588 into RA 0, of course, anyhow, plus ID. ID is equal to 0.808 into XD. XD is equal to how much XD? 0.8, no? XD. Yes, XD is equal to 0.8. 0.8. Yeah. So therefore, that E is equal to how much? E is equal to 1.603 per unit. Therefore, E is equal to 1.603 per unit value. This is one answer, E. E. Now, regulation. If you want to find regulation, what is the regulation? Regulation is equal to E minus V by V into 100 into 100. What is E? E is equal to 1.603 minus 1 by 1 into 100. So it is equal to 60.3%. So voltage regulation is 60.3%. Right? Yeah. And let me give one question, gate question. This is not gate question. Just have given one question. So mainly gate examination, most of the questions he will try to give per unit values, per unit, because easy calculations, per unit easy calculation. But even in the examination, he may be given numericals. So for example, V is equal to 400 volts, say, line voltage, unless otherwise it will be line voltage. So you have to convert that into per phase. Whenever you are substituting in any equation, they must be per phase values, per phase. Okay, then substitute 400 star connection, say 400 divided by root 3, substitute, because always XD XQ value will be given per phase. Of course, here per unit values are given. In a general question, any type, I have given in the material, you just do it. Or else any textbook you take, this type of problems are available, very important. Okay, yeah. Let me give one question, gate question I will give. It's a GATE 2011 examination for 2 marks. The question is an alternator. An alternator with XD is equal to 1.2 per unit, 1.2 per unit. XQ is equal to 1 per unit. XQ is equal to 1 per unit. RA is equal to 0. RA is equal to 0. If the alternator is delivering rated kVA, the alternator is delivering rated kVA at rated voltage. Rated kVA at rated voltage. Rated voltage. Then its power angle is rated voltage at UPF. Then its power angle is A bit. A bit 30 degrees, B bit 45 degrees, C bit 60 degrees, D bit 90 degrees. Tell me the answer for this. All of you try to do it. Tell me answer for this. I will give 1 minute, you have to answer. Yeah. See the answer. Tell me the answer. Everyone has to try. Okay. Just a minute. I'm forwarding. Completed? Yeah. So tell me what is your answer? Anyone have got your answer? Yeah. Yes, some of you are asking the armature reaction is proportional to XA. Yes, armature reaction is proportional to XA flux only, armature flux only. Answer is very good. C. Correct. Correct. Very simple question now. For this calculator also not required. Okay. See, the solution is V is equal to 1 per unit. IA also 1 per unit. Because it is given rated kVA. If half rated kVA is given, you need to take IA will be 0.5. IA will be 0.5. Right? Yeah. So then power factor UPF, no? UPF. Substitute tan psi. Tan psi is equal to V sin phi plus IA x cube divided by V cos phi plus IA RA. V cos phi plus IA RA. Now substitute here V 1. Sin phi 0. Sin phi 0. IA 1. X cube also 1 divided by V cos phi. 1 into power factor 1. 1 into 0. That is equal to 1 finally. Numerator, denominator, that is 1. Therefore, psi is equal to how much? From this psi is equal to 45 degrees. Psi 45. But we know psi is equal to phi plus delta. Therefore, what is delta? Delta is equal to psi minus phi. Psi is anyhow it is 45 and phi is 0. Unity power factor, no, phi 0. So that is equal to delta 45 degrees. So the delta is equal to 45 degrees. Answer is B. So this type, how simple question you see, 2 marks he has given. Okay, on salient pole machine, problems are fixed. Right? And same questions also in GATE 2016 he has given, and 2000 on synchronous motors also similar questions. But synchronous motors, what is the equations, you know? Just plus is there, where plus is there, it is minus. Where plus is there, it is minus. Therefore, let me write here itself for easy understanding purpose to remember. I want to compare both generator and also motor. Problem also, handling problem is also same. For easy understanding purpose, I want to write the 2 equations here itself for generator and also motor. See, for synchronous motor and generator is for salient pole synchronous generator. For salient pole synchronous generator, alternator, you know. For that, what is that? Phi is the angle between. Delta is the angle between E and V. Phi is the angle between V and IA. Psi is the angle between E and IA. Psi is equal to phi plus or minus delta. Phi plus or minus delta. Plus for lagging power factor and also UPF plus, minus is for leading power factor. Okay. Now similarly, ID is equal to IA sin psi. ID is equal to IA sin psi. IQ is equal to IA cos psi. And tan psi is equal to V sin phi plus IA x cube divided by V cos phi plus IA RA. This is another relations. Of course, once again I'm writing plus for lagging power factor and UPF. Minus is for leading power factor. Now last equation, what is that? E is equal to V cos delta plus IQ RA plus or minus ID XD. Plus for lagging power factor and UPF. Minus is for leading power factor. Okay. Leading perfector. This for generator, na? Motor, I am coming to the motor. For motor, see, for salient pole synchronous motor. For salient pole synchronous motor, for salient pole synchronous motor, wherever plus is there, you write minus. The alternator, I am writing left side, na? Alternator. Motor, it is quite opposite. Where plus is there, simply replace with interchange sign, plus minus. Okay, dear students, see, delta is the angle between E and V. Motor also same. Motor, what is the delta? Back EMF, EB and V. Phi same, power factor. Psi, EB and IA. But the psi is equal to phi minus R plus delta. Alternator to plus R minus delta. But motor minus R, phi minus R plus delta. Minus for lagging power factor, plus for leading and UPF. Plus for leading and UPF. UPF always use plus, that's all. ID same, IQ also same. But tan psi is equal to V sin phi minus IA x cube. Here it is plus or minus, na? Plus or minus, plus for lagging power factor, minus for leading power factor. But motor minus R plus, plus or minus instead of that, minus R plus, V cos phi in the denominator, minus IA RA, not plus, minus IA RA. And E is equal to V cos delta, minus IQ RA, alternator plus kada, here minus IQ RA, minus R plus IDXD. So wherever plus is there, simply write minus. So therefore, let me write here for easy understanding purpose. So delta is the angle between E and IA, phi is the angle between V and IA, psi is the angle between E and IA. EB and IA. Psi is equal to phi minus R plus delta, minus R plus delta, minus for lagging power factor, plus for leading power factor and UPF, leading power factor and also UPF. UPF also same. ID same. ID is equal to IA sin psi. IQ is equal to IA cos psi. It is same. And tan psi is equal to V sin phi minus R plus IA x cube divided by V cos phi minus IA RA. Minus IA RA. Minus IA RA. Minus is for lagging power factor, plus is for leading power factor and also UPF and UPF. UPF always plus. Similarly, E is equal to V cos delta. V cos delta minus IQ RA minus R plus IDXD. Minus is for lagging power factor, plus is for leading power factor and also UPF. Right? So these are the important relations. Synchronous motor also you can find. We are going to do at the time of synchronous motor. Why I am writing? Easy to remember. Okay, easy to remember. Generator and motor. Yeah. Okay. Fine. Now, the next topic is, you have taken, na? Are you ready? Yes. Sir, delta is wrong in motor. No, no, no. That is same. Equation will take care about. You don't see from the phasor diagram. Equation, it will come answer right only. It's verified. It will be same. Where plus is there, minus. The equation will take care about. You can do the problems and see the answer, then you will get the same thing. Delta should be between E and V. In case of motor, yes. Delta is angle between. Oh. Right. This is E and V. Delta is the angle between E and V. Please correct it. E and V. Delta is the angle between E and V. Phi is the V and IA. Of course, delta may be negative in the case of motor, even though delta positive. Please correct this. This is E and V. Delta is the angle between E and V. Phi is angle. The motor, what is the power factor? Input power factor, supply power factor. Psi is the angle between EB and IA. Okay. Yeah. We are going to the problems at the time of synchronous motor. These equations are valid. Equation, blindly follow the equation, you will get the answer. Don't think from phasor diagram, lagging power factor, leading power factor, when phi is greater than delta. At that time, you will get confused if you take phasor diagram every time. Not necessary. That's the reason I am making simplifying. Simply arithmetic differences we are coming. We are coming just magnitudes. Magnitudes. Substitute, you will get the answer. Okay? Yeah. Now, let us see the next topic. Next topic is measurement of XD and XQ. That is nothing but slip test. Slip test. Measurement of XD and XQ. Okay? Slip test. Slip test. That is measurement of XD and XQ. Measurement of XD and XQ. XD and XQ. The XD and XQ can be measured by conducting the slip test. So first what I am going to do is, I will draw the diagrams. Okay. I will draw the diagrams and then we will go for break. After that we will discuss, because so more diagrams will be there. You also just observe, and after the break, we will have the continued explanation. Almost so nearly 40-45 minutes discussion will be there on that. If I draw the diagram and explain, say, it will be bits. Discontinuity will come. So for having the continuous discussion, first let me draw the diagram. You also note down. A slip test, XD, XQ can be measured by conducting the slip test. Okay. See, for that, this is the three-phase variac. Three-phase variac. Ammeter. This is salient pole alternator. A voltmeter. Field winding is open circuited. The field winding is open circuited. and that will be driven. That will be driven at less than synchronous speed. The prime mover is driven at less than synchronous speed. With the DC motor, say, the DC motor, we can rotate that at less than DC motor or any prime mover. Say DC motor, I am taking DC motor. It is driven, NR is less than NS. NR is less than NS. This is ammeter, measures current. This is a voltmeter. In this three-phase supply, three-phase AC supply. Three-phase AC supply, say frequency is equal to some 50 hertz, say 50 hertz. This is the three-phase variac. Three-phase variac. Three-phase variac. A reduced voltage is applied. A reduced voltage, 20 to 25% of V rated. 20 to 25% of V rated is applied to the armature. Is applied to the armature. This is salient pole alternator. Salient pole synchronous machine. Salient pole synchronous machine. And salient pole machine. Actually, there I have drawn diagram. Na? Yes. Here, field winding is open circuited, of course. Field winding is open circuited. No DC excitation is given. No DC excitation, simply open circuited. Right? But this is, we are supplying from three-phase variac. This is from three-phase variac. Reduced voltage from three-phase variac. They are drawing the currents. Based on that, here north pole and south poles will form. Armature poles. Say this north pole and this south pole. But rotor is driven at less than synchronous speed. NR is less than NS. NR less than NS. We are rotating less than synchronous speed. Okay. And what we are doing, once adjusted the flux constant. Flux constant means E by F ratio constant. Armature flux phi A. Armature flux phi A is equal to armature MMF divided by reluctance. Reluctance is proportional to air gap length. But that will be flux is constant. Why? Because V by F ratio is constant. V by F ratio will be constant. So once we are adjusted voltage, because V by F ratio is constant. But phi A is equal to armature current into number of turns divided by reluctance. That is proportional to area. It will be constant. Don't worry, I am going to explain each and everything. Now we are going to take for two cases. This will be driven at less than synchronous speed. Yeah. And two cases we are going to see. Two cases. Case 1. Case 1. When armature poles or MMF align with D axis. Align with direct axis. Align with direct axis. And case 2, second case, case 2 is armature poles align with quadrature axis. When armature poles are MMF align with Q axis, quadrature axis. Align with quadrature axis. We are going to observe for 2 cases. Poles will be aligned with direct axis. Some other instant poles will align with quadrature axis. That is what I am going to write. Align with so poles are aligned with, this is north pole, say south pole, align with quadrature axis. These poles are rotating continuously. Poles are rotating. Okay. And in this, due to this, the current variation. The last diagram, then we go for break, then we will discuss. So how it is happening, that we will see. The variation of armature currents and their MMFs yeah. This is going to be current variation. Current variation. The currents are Inside also sinusoidal waveform. And lastly, yeah, this is the armature voltage waveform. Armature voltage waveforms. Yeah. So this is V, this is IA, armature current, and this is E, induced EMF E, induced EMF E. All they are with respect to omega t or time t. Omega t with respect to time t. Omega t with respect to time t. This is induced EMF. So this is the induced EMF in the open field winding. Induced EMF in open field winding. Open field winding. Whereas this is envelope of armature voltage. Envelope of armature current IA. Armature current IA. But the inside of this is armature current IA. Armature current IA. Armature current IA. Whereas this is envelope of voltage. Envelope of armature voltage. Armature voltage V. V. Inside of that, this is nothing but armature voltage. Armature voltage V. Okay. Yeah, these diagrams are sufficient. Now, after the break, we are going to see in detail discussion about the slip test. Slip test, right? Very clearly we will discuss. So I have kept ready all the diagrams so that after the break we will see the continuous discussion, right? So these are the diagrams. This will be sufficient. Okay. So now let us take the break for 20 minutes. Class will start at 7:27. Yes, 7:47. 7:47 p.m. Yeah. Yes. Some of the students are asking, psi. Psi is the internal power factor angle. Psi is called what? Internal power factor angle. Phi is the load power factor angle. Phi is the angle between V and IA. Psi is the angle between E and IA. It is internal power factor angle. Okay. Psi is internal power factor angle. I have given at the time of phasor diagram. Okay. Now are you ready? Came all the students? Yeah, just I'm seeing. Okay. Right. Shall we start? Yeah. Yes. Hmm. Yes. Okay. See, dear students, this is the diagram, circuit diagram to measure the XD and XQ. XD and XQ. Okay. This is three-phase variac. Three-phase variac means what? Auto transformer. Three-phase variac, auto transformer. And from this auto transformer, what we are doing? A reduced voltage is applied to the alternator. This is armature. This is actually armature winding. I am showing with star connection. This is the field winding. Field winding. Of course, it is open circuited. Open circuited. Right? Yeah. See, to this armature winding, we are applying a reduced voltage from the three-phase variac. This is a three-phase variac. We are applying a reduced voltage to this armature. How much voltage? Reduced voltage 20 to 25% of V rated. 20 to 25% of V rated is applied to the armature. So for example, rated voltage some 400 volts say. Rated voltage 400, line voltage say, I will apply 20%. 20% of 400 means how much? 80 volts. 20% 80 volts. 25% 100 volts. 100 volts. So we are going to apply 80 or some 100 volts, say 100 volts. 100 volts. But once it is adjusted, the voltage is kept constant. Once we are adjusted that voltage 20%, 25%, 100 volts, say, that is voltage is kept constant. Later we are not going to change. Voltage is kept constant. And frequency anyhow constant. Frequency constant. So V by F ratio is constant. We are keeping constant voltage and constant frequency. 100 volts I am supplying, frequency 50 hertz. Because frequency, supply frequency 50 hertz, the output frequency also 50 hertz. Right? So voltage and frequency kept constant. Of course, reduced voltage, but once adjusted, that voltage is kept constant. Fine? Yeah, V by F ratio is constant. And when V by F ratio is constant, flux in the machine will be constant. Flux in the machine will be constant, right? Yes. In our armature, flux is going to be constant. Flux will be constant. Why? You may be knowing that flux Y constant. Because E is equal to 4.44 Kp Kd phi ft. That is proportional to V. That is nearly equal to V. Therefore, what is flux? Flux is equal to 1 by 4.44 Kp Kd into T, V by F, V by F. So flux is proportional to V by F. Flux is proportional to V by F ratio. If V and F is constant, no, both voltage and frequency constant, say, then flux will be constant, right? V by F is constant, therefore flux also constant. Flux will be constant, right? So this is one of the important statements, right? Yeah. Okay. Yeah. Now see, we are applying a reduced voltage, but that is kept constant. So alternator armature is supplied with 100 volts, 50 Hz frequency. Now field winding is open circuited. No DC excitation is given. Simply it is open circuited, field winding open circuited, and that will be driven with the DC motor or any prime mover. Just I am taking DC motor, you can take anything, a prime mover, that will be driven at less than, NR is less than NS. NR is less than NS. So for example, synchronous speed is 3000 RPM, say 3000, we are rotating some 2500, or synchronous speed is some 1500 RPM, say we will rotate less than 1500. Less than or even more than also does not matter, but rotor has to be driven less than or more than, but not at synchronous speed, And we are going to see all the reasonings. What is the reason? Why to apply a reduced voltage? Why to apply a reduced voltage to the armature? And why field winding has to be open circuited? And why to rotate it less than synchronous speed? All these things we are going to see. I will come at the reasonings at the end. I will ask you people at that time, you are in a position to explain that reasons and you can easily understand. If I right now, if you say you can't understand anything, at the end I will discuss. Okay. See, this is our circuit diagram. Here, the same thing only. This is our alternator physical diagram. This is a physical diagram and this is circuit. So in this physical diagram, I am applying a reduced voltage from three-phase variac. We are applying from three-phase variac to our armature winding. This is the rotor. Rotor is simply open circuited. Okay, but that will be driven with prime mover DC motor at less than synchronous speed. NR is less than NS. That NR is less than NS. Okay. For example, yeah, see, when supply is given, what will happen? When three-phase supply is given to the armature, of course it may be reduced, but when three-phase currents, it will draw the currents, no? Yes. When balanced currents is observing, that balanced winding exists in the balanced winding. Balanced currents are there, balanced winding. Rotating magnetic field will be produced. Okay. Just like for induction motor or synchronous motor, even any motor it may be. But here the machine may be not acting as a generator, not acting as a motor. It is a synchronous machine. I am not rotating at synchronous speed. Dear student, I am not operating this machine as a synchronous machine because no DC excitation. I am not rotating at synchronous speed. I am just testing the machine. I am taking the machine. I want to measure XD and XQ. For that, we have to do like this only. We will see why to do like that. So, reduced voltage is given to the armature, and when supply it is taking, it will draw the currents, then it will produce the rotating magnetic poles. Stator poles will form, na? Yes, the stator poles will form north pole and south pole, and they will rotate at synchronous speed. For example, synchronous speed is 3000 RPM, say. Two-pole machine means at what speed? Rotate 3000 RPM. And NR, but rotor is rotating at less than synchronous speed. Rotor is rotating some 2500 RPM, say. Rotor is rotating only 2500 RPM. Then there will be relative motion between both armature field and rotor. See, important thing here, right now, whatever I have shown, the poles, armature poles are aligned with direct axis. Armature poles are aligned with direct axis, but no poles on the rotor, no poles on the rotor. Only stator poles, armature poles, they are rotating at 3000 RPM. But our rotor is slower. Right now it is aligned with the direct axis, but after some time, angle between these two will changes. Both rotating fine, but one is moving faster. Angle between both will be changes. Both changes. Right now 0 degrees. After some time 10 degrees, 20 degrees, 30 degrees, 90 degrees means poles are armature poles are aligned with quadrature axis. And another 90 degrees, 180 degrees means poles are aligned with direct axis. Another 180 degrees, another 90 degrees, quadrature axis, another 90 degrees, direct axis. The angle between the armature poles and direct axis rotor poles keep on changes. Angles are keep on changes. And keep on changes means once armature poles are aligned with direct axis, after some time definitely it will align with quadrature axis. Another sometime align with direct axis. Like that, angles are keep on changes. And so I would like to take two instants. I would like to take two instants. What is that? Once armature poles are aligned with the direct axis, and another one is armature poles are aligned with quadrature axis. And at these two instants, we will measure the voltmeter and ammeter reading. These two instants, where armature poles direct axis, quadrature axis. So we will measure voltage and current. With the knowledge of voltmeter and ammeter reading, we can measure the XD and XQ. Okay, yes, that's what we are going to see. But before that, the V by F ratio constant, I am applying the reduced voltage 100 volts, that is kept to constant, frequency constant. Then what about the flux? The flux is constant. Phi A is equal to armature MMF by reluctance. Reluctance is proportional to air gap, but flux will be constant. Why? V by F ratio constant. But flux is equal to what? Current into tons, ampere tons, MMF. MMF divided by reluctance, current into tons by reluctance, that will be constant. So this is the important point. With this only, we will recollect everything. We can recollect everything that we are going to see. Okay. Yeah. So coming to the diagram, as I told, armature poles align with the direct axis. After some time, it will align with quadrature axis. So let us take two instants. These are the two instants I have taken. Armature poles align with the first diagram aligned with the direct axis. Armature poles are aligned with quadrature axis. But these poles are continuously rotating. Poles are continuously rotating. Rotor also rotating. Rotor also rotating. Fine. Rotor also rotating. Don't think they are not stationary. But we are taking at one particular instant. One particular instant. Okay. Yeah. Now, so case 1, when armature poles align with the direct axis, what is the flux direction? See, the flux direction is from north to south. It is taken from north to south. Is the flux direction north to south and north to south. This is the flux direction. Yeah. But this flux is finding minimum reluctance, This flux is finding minimum reluctance. Reluctance is minimum. So when reluctance is minimum, what will happen? Flux is constant. Mainly, our relation, as I told earlier, flux is equal to what? Armature MMF divided by reluctance. That is proportional to air gap. That will be constant. Therefore, armature flux only there in our machine. Which flux is there in our machine? Armature flux. No main field flux because no DC excitation. But that phi is equal to IA into tons by reluctance proportional to air gap. That must be constant. So mainly I will take with this relation. Let us explain. Yeah, you have to see this relation mainly. Listen. So what is going to be happen here? Dear students, see. Armature poles are aligned with the direct axis. So air gap is minimum. The flux offer minimum reluctance. Air gap is minimum. When air gap is minimum means reluctance minimum. And when reluctance is minimum, denominator is minimum. Denominator is minimum. When denominator is minimum means numerator also minimum. No? We establish the constant flux. When air gap is minimum, reluctance minimum, then current drawn from the supply also minimum. Therefore, ammeter shows minimum reading. Voltmeter shows maximum reading. Ammeter shows minimum. Earlier, this is ammeter is there na? When aligned with the direct axis, ammeter shows minimum reading, but voltmeter shows maximum reading. Why? Because current drawn from the variac is minimum. Current drawn from the variac is minimum. So minimum drop in the reactance. The drop in this here is a drop. Drop in this. Drop is varying. We are not changing the voltage. Drop in the variac. Drop is depends upon what? Current, no? It is depends on the current. But here we are drawing the current is minimum current. So drop is minimum in the variac. When drop is minimum means output voltage is maximum. Voltage is more. Voltage is more. Okay. So I hope you understood. Air gap. So once armature poles align with the D axis, let me write these things. When armature poles align with the D axis, air gap is minimum. Air gap is minimum. Therefore, reluctance is minimum. Reluctance is minimum. Minimum. So to establish the constant flux, the current drawn from the supply, is minimum. Current drawn from the supply is minimum. Therefore, ammeter shows minimum reading. Ammeter shows minimum reading, and voltmeter shows maximum reading. Voltmeter shows maximum reading. Why? Because drop in the variac is minimum. Drop in variac is minimum. Drop in variac minimum. When drop minimum means voltage is maximum. Voltage is maximum. Right? Yeah. So therefore, IA, ammeter reading, IA is minimum, but voltage is maximum along D axis, along direct axis. Therefore, what is XCD? XCD is equal to V maximum per phase. V maximum per phase divided by IA minimum per phase. IA minimum per phase. That is XCD. Okay, that is XCD. XCD is equal to V maximum per phase divided by IA minimum per phase. Is XCD, direct axis reactance. In this condition, if you take ammeter and voltmeter reading, how they will be? Ammeter reading and voltmeter reading, if you take, this is ammeter, this is voltmeter. Ammeter reading is minimum, IA minimum, but voltmeter reading is maximum. Voltage is maximum. Clear? Why voltage maximum means drop in the variac is less. Drop in variac is minimum. Voltage I am not changing. Drop based on the drop. So that is XD. XD is equal to V maximum per phase by IA minimum per phase. Similarly, next. Then coming to the second case, when armature poles or MMF align with quadrature axis. Case 2. When this armature poles align with both rotating, fine. Both rotating. One particular instant, armature poles align with quadrature axis. At that time, this is the flux direction. This is the flux direction. Flux is passing from north to south. This is a flux path. Flux path. Okay, this is a flux, armature flux. But now, armature flux find maximum reluctance. This is the phi, no? Armature flux phi. It is finding maximum reluctance. Reluctance is maximum. Again come to that. When reluctance is maximum means from this relation, quadrature axis, air gap maximum, reluctance maximum, denominator is maximum, the numerator also must be maximum. But numerator which is maximum? Current. T constant. Okay, when flux changes, air gap changes, current also changes. Because ratio is constant. When denominator, air gap is maximum, quadrature axis, air gap maximum, reluctance maximum, to establish the constant flux, current drawn from the supply also maximum. Current drawn from the supply is maximum. Right? Yes. So therefore, ammeter shows maximum reading, voltmeter shows minimum reading. Yeah. See here, when armature poles are in with, air gap is maximum. Air gap is maximum. Therefore, reluctance is maximum. Reluctance is maximum. Therefore, to establish the constant flux, the current drawn from the supply, is maximum. Current drawn from supply is maximum. Therefore, ammeter shows maximum reading. But voltmeter shows minimum reading. Why minimum reading? Because drop in the variac. Drop in variac is maximum. Drop is more means voltage is less. So that's the reason. Then IA is equal to how much? IA. See, IA is maximum. Voltage is minimum along quadrature axis. Therefore, what is XQ? XQ is equal to voltage by current. Reactance is equal to voltage by current. So we know voltage and current. V minimum divided by V minimum per phase. Of course, they may be given directly line voltages. We need to convert into per phase. V minimum per phase divided by IA maximum per phase. Okay. IA maximum per phase. This is XQ. Okay. Yeah. Along the quadrature axis. Now, how the readings they will be? So, ammeter and voltmeter reading. If you take this is ammeter and voltmeter reading. Voltmeter reading, ammeter reading is maximum. IA is maximum. But voltmeter reading is minimum. Okay. So this is XD and XQ. But at the same time, you can find you can find here which is more, XD more or XQ more? Is it XD is more or XQ is more? XD will be more. From the equation, V maximum divided by, it is V maximum by I minimum. More voltage, less current. But whereas here, less voltage, more current. So definitely XD will be greater than the XQ. From these relations, we can get XD. So this is the way to measure XD and XQ. So simply, we will measure from this diagram, no? This diagram. When we are rotating, so it is aligned with the direct axis, quadrature axis. We can take two readings, minimum value, maximum value. But in between, the ammeter and voltmeter, they will oscillate. Don't think it is not only once minimum, once maximum, not like that. So they will oscillate like this. Ammeter reading is first minimum direct axis, voltage maximum. And again, when they are coming, so as air gap increases, they will minimum, maximum. Okay, this is minimum, this is maximum, minimum, maximum. They will keep on changes. Voltmeter, ammeter readings will oscillate. Look, 0 degrees, na, direct axis, it is minimum. And after some time, what happened? This is 0. Na? After some time, angle increases, some 10 degrees, 20 degrees. When this is 0 degrees, 10 degrees means current increases, 20 degrees increases, 30 degrees. 90 degrees, it is again maximum, 90 degrees maximum. 90 to 120 decreases, 140 decreases, again 180 minimum, because again it is going to be direct axis. Another 90 degrees, again quadrature axis. So it changes. I am observing only direct axis, quadrature axis, but in between angle also 10 degrees, 20 degrees like that. Yes, 0 degrees to when it is going, current gradually increases, and after 90 degrees it will come to maximum, and another 90 degrees will come to minimum. So keep on changes there. So we will note down minimum, maximum readings, then you can find the XD and XQ. Okay, so this is the procedure. Now with this, what type of questions you can expect on this? You can expect on this. See, the question is, in one of the examination, the question is like this. The question is like this. Question is, and first of all, okay, before going to that question, see, in this current is minimum, maximum, na? Can you tell me what is this current? Can you tell me, is this current is it a active component or reactive component? Is it active component or reactive component? It is the reactive component. Reactive component, because it is only magnetizing the core. Na? It is only magnetizing the armature core. It is producing the armature flux. Armature flux. That is nothing but magnetizing current, reactive current. And you may be knowing the magnetizing current is proportional to air gap length. In transformer, air gap is minimum, magnetizing current is less, but induction motor, air gap is there. So that's the reason the magnetizing current is 30 parts per 40%. If still air gap increases, it will draw the large magnetizing current. So in this, our armature current is Ia sin phi component, that is reactive component, that is only magnetizing, it is producing the armature flux. Now you can remember very easily, this is the main key point. What is that? When armature poles are aligned with direct axis, see, armature poles are aligned with the direct axis, air gap minimum. That's the reason the magnetizing current drawn from the supply is minimum. But when aligned with quadrature axis means air gap maximum. So current drawn, magnetizing current also will be maximum, because V by F ratio constant, flux will be same. Okay, yes. So current is minimum, direct axis. Anyhow, voltage maximum, and current is maximum, voltage minimum. So the question is, the question in your examination, question is like this. The question, during the slip test, the current is, the armature current is minimum. When armature poles are MMF, align with A bit D axis, B bit Q axis, C bit 45 degrees to D axis and 45 degrees to Q axis. What is your answer? During the slip test, the armature current is minimum. When armature poles align with the D axis or align with Q axis. What is the answer? The answer will be D axis. We know already. Current is minimum. When air gap is minimum, current is minimum. D axis, current will be minimum. Similarly, during slip test, while we are conducting the slip test, right? There will be an EMF is induced in the field winding. An EMF will be induced in the open field winding, correct? Here we are simply open circuit, this field winding. But there is a relative motion is there between this and this. An EMF will be induced here or not? Definitely an EMF will be induced in this. An EMF will be induced in the field winding. Okay? EMF is induced. And that induced EMF, yeah, an EMF will be induced in this. Why? Because armature poles are rotating at a synchronous speed, but rotor winding rotating at less than synchronous speed. That is 3000, this is some 2500, or that is 1500, say this is 1400. So what is the relative speed between both? Slip speed. Due to that, an EMF is induced. The rotor winding, field winding will cut the armature flux, and EMF is induced in the field winding, open field winding. That induced EMF, is it AC or DC? Tell me. Induced EMF in the field winding is AC or DC? It is AC only. Induced EMF, no question of DC. Induced EMF is AC. Okay, we are not giving DC. Forget about field winding is, we are not, no question of giving DC excitation in this experiment. So induced EMF is AC in the field winding, which is AC. Sinusoidal, shape of the waveform is sinusoidal. At what frequency? Slip frequency. Slip frequency. That's the question. Question is like this. During the slip test, induced EMF in the open field winding is A bit AC, B bit DC, AC sinusoidal, AC rectangular, or AC slip frequency, AC supply frequency, like that. Only one statement. Induced EMF in the open field winding is AC sinusoidal at slip frequency. Slip frequency. I am writing the statement. During the slip test, an EMF will be induced. An EMF will be induced in the open field winding. An EMF will be induced in the open field winding. Open field winding, which is AC, sinusoidal. AC sinusoidal at slip frequency. Slip frequency. AC sinusoidal slip frequency. Yes. Sinusoidal slip frequency. Okay. Yeah. That is itself E. See? E. In this diagram, you can find, dear students, this is itself induced EMF at slip frequency. Induced EMF at what frequency? At slip frequency, SF. That will be at SF. This induced EMF AC sinusoidal at slip frequency. Right. Now here question is, another question will be, induced EMF is AC, okay. AC means induced EMF is 0, induced EMF is maximum, induced EMF is 0, maximum 0. There keep on changes, na? Yes, there keep on changes. But at what instant induced EMF is? At what instant induced EMF is minimum and induced EMF is maximum? So induced EMF is 0 here. When that instant occurs, that induced EMF will be 0 along the direct axis or quadrature axis. Here also induced EMF is direct axis or quadrature axis. That will be, see, that will be, listen, when armature poles align with direct axis, all the armature flux is passing inside of the coil. This is a coil. All flux is passing inside of the coil. When all flux passing, flux linkages is maximum. Flux linkage is maximum. When flux linkage is maximum means what is induced EMF? Induced EMF is minimum. Flux linkage, all flux, armature flux. Here students, here we are finding induced EMF in the field winding. General cases, it is normally working as alternator. We will give DC current and poles will form. They will rotate. They cut the flux in the armature conductor. EMF is induced in the armature winding. General case. I am not talking about that induced EMF in the armature winding. I am discussing about induced EMF in the field winding. We are armature flux cuts by the field winding. So at this first case, all armature flux are passing inside of the coil. This is a coil means all flux lines are passing inside of the coil. All flux lines are passing inside of the coil. So flux linkages is maximum. All armature flux lines are passing through the coil. Flux linkages is maximum. But when flux linkages is maximum, what is induced EMF? Flux linkages maximum means induced EMF will be minimum, 0. So here flux linkages is maximum. Flux linkages what? All flux lines are passing, no? Yes, maximum. But induced EMF is minimum. Induced EMF is equal to d psi by dt. That will be 0. That will be 0. Okay? Yeah. Psi maximum, E will be 0. Flux linkage is 0. Whereas in the second case, flux linkages is minimum, but induced EMF is maximum. Okay. Not necessary to view that isometric view. Already I have given very beginning classes. If all flux lines are passes through the coil, do you remember at the time of EMF equation I have explained? If all the flux lines are passing inside of the coil, they do not cut. Simply the coil sides will move parallel. So here it is given, all flux lines are passes inside of the coil. No flux lines are cutting. Induced EMF is minimum. But in this case, induced EMF is maximum. So see, along the D axis, I can decide this is the D axis, no? Yes, this is the D axis. D axis where EMF is 0. But Q axis EMF is maximum. That is Q axis is maximum. Again D axis minimum. Again Q axis it is maximum. And again D axis it is minimum. These are the axes. Direct axis and quadrature axis. Okay, D axis and Q axis. Right? Yeah. Now, the question in your examination, based on this, the question is like this. The question is, during the slip test, the induced EMF, during the slip test, the induced EMF in the open field winding. Induced EMF in the open field winding. Induced EMF in the open field winding is A bit. 0 for XD, 0 for XD, B bit. 0 for XQ, C bit. Maximum positive for XD, D bit. Maximum positive for XD and maximum positive for XQ. Maximum positive for XQ. Okay. Just a minute, I will come. There is some noise is going on. I will inform and you will come within a minute. Tell me the answer for this. Okay. Yeah, sorry. There was some disturbance is going on. The outside inform. Right. What's your answer? Tell me. During the slip test, the induced EMF in the open field winding is 0 for XD, 0 for XQ, maximum positive for XD, maximum positive for XQ. So what is your answer? Yeah. See, in this 0 for XD is correct. Maximum positive for XQ is also correct. But maximum negative also, na? Maximum negative also there. It is AC, na? Maximum positive, maximum negative also. So therefore, answer is 0 is always 0, na? Yes, answer will be 0. 0 for XD. 0 for XD. Right? Yeah. Now, see. And coming to here, these currents are there, na? This armature current, inside of that, this armature current. Along the direct axis, dear students, you can find along the direct axis, the armature current is minimum. Quadrature axis, armature current is maximum. Maximum. This is envelope of armature current. Envelope of armature current. Envelope. Envelope means what? By joining all the peak values. They are simply joining all the peak values. See, these are maximum values of armature current. Maximum values of armature current. All peak values by joining. This is said to be positive envelope. We are joining all positive peaks, positive envelope. And these are the negative envelope, negative maximum. By joining negative maximum. See, where is the current maximum? The current maximum will be, this is current maximum. This is the current maximum. This is current maximum. Current waveform is maximum. But whereas here current is minimum. In this wave, this current is minimum. Current is minimum. But where is the voltage you see? Voltage is here, it is minimum. Voltage waveform minimum. And here voltage waveform is maximum. Voltage waveform is maximum. This is one wave. That is AC only, sinusoidal waveform. Current is also sinusoidal. This is sine wave. This is sine wave only. But envelope means by joining all the maximum values, all negative maximums. Similarly, inside this is there, na? This is armature voltage. This armature voltage, whereas this is envelope of armature, envelope. Here is also the, whenever current is minimum, dear students, see along direct axis, current is minimum, but voltage is maximum. Voltage is maximum. Similarly, quadrature axis, the current is maximum, but voltage is minimum. Voltage is minimum. Okay? Yeah. This is a waveform that you can also see in the CRO, oscillograms. They are said to be called what? Oscillograms. You can also observe these things from CRO also. But I want to measure from CRO, say, by using this, yes, I can say this is voltage waveform. Peak value is there, na? Peak value. Vm by root 2, I will get RMS value. Vm by root 2. And current also, current waveform, maximum value, that divided by root 2. So this divided by root 2 divided by that divided by root 2, you will get the XD. XD means what is the voltage along that, what is the current along that. Okay, yeah. And on this waveform, the question is, important point is, see, this is the slip cycle. This is the slip cycle. Slip cycle. Slip frequency, na? What is the time period? T. This time period is T. When that time period is T means, what is the time period of this? Tell me, what is the time period of this? This is T by 2. T by 2. Up to here, T by 2. This is nothing but T by 2. From here to here, T by 2. So, frequency is, if the induced EMF frequency is slip frequency, what is envelope frequency? Frequency of this envelope, time period is a minimum, maximum, minimum. Again, it is repeating. The waveform is repeating from here onwards, no? Repeating here and again here. So, its a time period is this much only, time period, T by 2. When T by 2 means what is the frequency? 2 times of slip. For this is the time period. For that, frequency is 2SF. But for this is the time period. So frequency is how much? 2 times of slip frequency. Time period is half. Frequency double. Frequency is double. So therefore, this is armature, envelope of armature 2SF. 2SF. And armature current will be supply frequency. It is at supply frequency only. It is at supply frequency. That is equal to F is equal to 50 Hz frequency. 50 Hz frequency. Correct? Time period is very less. More cycles. Within half cycles, there are many cycles. Supply frequency. Armature current is supply frequency only, na? Why? Because see this diagram. See this diagram. I am drawing the current from this. This is 50 Hz. What is the output of the variac? Also 50. Voltmeter reading also frequency 50 only. Current and voltage 50. They are same. Supply frequency only. Supply frequency. That's the reason you can find many cycles. Many cycles. Similarly, envelope of armature voltage is 2SF. Two envelopes are 2SF. But what is this? It will be supply frequency. This is again at supply frequency. F is equal to 50 Hz frequency. Okay. This is the question. Match the following. Previous your ESC examination. Match the following. During the slip test, induced EMF in open field winding, armature current, envelope of armature current, and armature voltage. They are SF, 2SF, F, like that. Very clear. Induced EMF is at slip times of frequency. 2 envelopes are 2SF. Armature current and voltages are supply frequency. Okay. Yeah. This is about the slip test. Fine. Yeah. And questions will be again. What are the type of question? E may be given ammeter, voltmeter reading, minimum reading, maximum reading. Previous ESC 2005 and 2008 examination has given slip test results. Slip test results, V minimum, V maximum, IA minimum, IA maximum. What is XD? What is XQ? That we know. XD is equal to maximum voltage by current, minimum current. XQ is equal to minimum by maximum. Right? Yeah. Yes. Then coming to the lastly, reasonings. See, reasonings. Yeah, we are going to complete quickly. Reasonings are like this. Reasonings. Slip test. During the slip test, we have applied reduced voltage. Okay, to the armature. Why reduced voltage? And why rotor has to be driven at less than synchronous speed? Rotor to be driven at less than synchronous speed. And why field winding has to be open circuited? Let us see all the reasonings. The reasoning is, if you rotate, rotor is rotated synchronous speed, what will happen? Tell me. If the rotor is rotated synchronous speed, what is going to happen? If you rotate rotor at synchronous speed, armature poles are rotating at synchronous speed. If rotor also rotated synchronous speed, it always find air gap is minimum only. Minimum only. Actually, what we have done, this is some synchronous speed, this is less than. For example, this is 3000, 2500 RPM say. Now, once it is aligned with the direct axis, after some time, angle changes, 0 degrees now, 0, 10, 20, 30, like that. Angle changes. So when angle changes, armature flux find very variable reluctance. But when both are rotating with the same speed, armature poles rotating at synchronous speed, if your rotor also rotating at synchronous speed, so both rotate together, always armature poles are always aligned with the direct axis. When always aligned with the direct axis, armature current is always minimum only, right? And we don't know it is minimum also. For example, by default, both are at some 30 degrees. And always that 30 degrees always maintained. Therefore, current is always constant. No variation of current. There is no variation of ammeter and voltmeter reading. You cannot find. Ammeter, voltmeter reading will be constant. Constant only. Constant means that voltage by that current is called some reactance will give. But is it direct axis or quadrature axis? You don't know. Okay. Ammeter reading, voltmeter reading constant. We cannot find. For example, once aligned with the direct axis, say only XD you will get. How can you get XQ? That's the reason what to do. So both will be driven at different speed. There must be, rotor must be driven less than synchronous speed. Then definitely once it is aligned with quadrature axis, direct axis, after some time definitely it will align with quadrature axis. Then ammeter and voltmeter reading, variation of ammeter and voltmeter reading. It is understood that when current is minimum means direct axis, when current is maximum it is quadrature axis. So why we are getting variation? Relative speed is there. But if relative speed is 0, there is no variation of ammeter and voltmeter reading. They will show the readings, but they are fixed. Then you cannot find XD and XQ. That's the reason compulsory rotor has to be driven less than synchronous speed. Even more than also does not matter. More than also you will get the same thing. Some slip must be required. Slip must be required. That's the reason this is called a slip test, dear students. That's the reason it is called slip test. Slip 0 means you cannot measure XD and XQ. During this experiment only, we will rotate our machine and some slip will be maintained. Okay, yes. That's the reason slip test. Number 1. So rotor has to be rotated less than or more than synchronous speed. If rotate synchronous speed, no variation of ammeter and voltmeter reading, not possible to measure XD and XQ. Number 1. Second one is, second reasoning, field winding is open circuited. Field winding is open circuited. Instead of that, if field winding is excited with DC, say, if I give DC supply, what is going to happen? When DC supply is given means, then poles will form. Rotor poles are going to be formed, na? Yes. Rotor poles will form. For example, this is south and north. When rotor poles are formed, both will be magnetically locked. Both will be magnetically locked and both will rotate at synchronous speed. It becomes synchronous motor now. When excited, stator poles, rotor poles, both are magnetically locked. It will rotate at synchronous speed. When it is rotated synchronous speed, no variation of ammeter and voltmeter reading. No variation, they are constant. Then how can you find XD, XQ? No. That's the reason there should not be any DC excitation. No. No excitation. There should not be any excitation. Correct? Yes. There should not be any excitation. Fine? Yes. And next, third one. We have to apply a reduced voltage to the armature. Reduced voltage. Why? Because if you apply rated voltage, what will be the current? Tell me. Current is equal to actually the current IA. IA is equal to V minus E divided by ZS. V minus E by ZS. Under actual loaded condition. But when excitation is 0, when excitation is 0, what is this E? This E will be 0. E0. When E0 means current is equal to simply V by ZS. V by ZS is very, very large because no EMF opposition. Why? Because no DC excitation, no main field flux cutting, right? Yes. So no opposition. Actually, motor V minus E by ZS or generator E minus V by ZS, but that E is missing. E is missing. That's the reason current will be very, very large. Very large. No EMF opposition. That's the reason you have to apply a reduced voltage. We have to apply this voltage will be less voltage. Less voltage. 20 to 25% is given. That is sufficient. Otherwise, rated voltage is given. Armature current is much more. The winding will get burned. Winding will get burned. Okay. That is the reason. And sometimes, dear students, see, sometimes the induced EMF will be much more in the open field winding. Much more. That E is there, na? Very large induced EMF sometimes. What may be the reason? Tell me. What may be the reason? Very large. Even you are rotating it slip speed only. That is 1500. This is 1400. But even though very large, what may be the reason? The reason is if phase sequence is not proper. If this is your rotor is rotating clockwise, okay. But if phase sequence of the your supply phase sequence is not same, armature poles may rotate opposite direction. It is 3000 RPM in counterclockwise direction rotating, say. But rotor is clockwise, armature poles phase sequence is different, say. then your rotation, your phase sequence is different. Both will rotate in opposite direction. Relative speed is nearly double the synchronous speed. Relative speed is nearly double the synchronous speed, then induced EMF is very large. At what frequency? Nearly double the supply frequency. You may get 100 edges nearly. You both rotate opposite. That's the reason phase sequence of your, whatever the supply is given, that phase sequence must be matched with your rotation. So that will be only difference of both. When rotate same direction, difference. If you rotate opposite direction, say, the difference will be sum of both. Okay. So let me write all these reasonings. Reasonings are reasonings. First one, during the slip test. During slip test, the rotor has to be driven. The rotor has to be driven at less than synchronous speed. Less than synchronous speed, or even more than synchronous speed, or even more than synchronous speed. More than synchronous speed. More than synchronous speed. Because if the rotor is driven at synchronous speed, the rotor is driven at synchronous speed. The rotor is driven at synchronous speed. There will be no variation of. There will be no variation of. There will be no variation of ammeter reading and voltmeter reading. Ammeter and voltmeter readings. There will be no variation of ammeter and voltmeter readings. No variation of ammeter voltmeter reading. Therefore, not possible to measure. Not possible to measure XD and XQ. Not possible to measure XD and XQ. Okay, that is one reason. Number one. And secondly, during the slip test, the field winding has to be open circuited. The field winding has to be open circuited. The field winding has to be open circuited because if the winding is excited, with DC, the rotor poles will form. The rotor poles will form and magnetically locked, They magnetically locked with stator poles. Comma rotated synchronous speed. Then no variation of ammeter and voltmeter readings. Therefore, not possible to measure XD and XQ. Not possible to measure XD and XQ. Not possible to measure XD and XQ. We cannot measure. Okay. Yeah. Next reason. Let us see. Another reasoning is during the slip test, a reduced voltage has to be applied. A reduced voltage has to be applied. A reduced voltage has to be applied to the armature. Because if the rated voltage is applied, the armature current will be much more. Because since there is no EMF opposition, since no DC excitation. Okay, there is no DC excitation. That's the reason armature current will be much more. Fine. Lastly, during slip test, sometimes the induced EMF in the open field winding, will be much more. Winding is much more. The reason is the armature field will rotate in opposite direction. That of rotor rotation. Then the relative speed between armature field and rotor winding is nearly double the synchronous speed, double the ns. Therefore, large induced EMF at double the supply frequency. In the open field winding. Okay. In the open field, these are the reasonings. That's the reason we have to do all the things. That is a procedure. This is a slip test, namely called slip. If slip is 0, say, you cannot measure XD and XQ. Some slip is required. Though it is a synchronous machine, we are not operating our machine as a synchronous machine. We are testing, we are measuring XD and XQ. If the slip test is conducted on cylindrical machine, what will happen? Tell me. If slip test is conducted on cylindrical machine, what is the reading? If slip test is conducted, what is the reading? Tell me. Can you get any reading? No. Yes. You will get the readings, but always they are constant. See, if slip test is conducted, on cylindrical machine, cylindrical rotor synchronous machine. Cylindrical rotor synchronous machine. Then what happened? What will happen? Tell me, what is going to be happen? Slip test is conducted on cylindrical rotor machine. What will happen? If you conduct a slip test on cylindrical rotor synchronous machine, this is cylindrical rotor synchronous machine. Say cylindrical rotor synchronous machine. Is a rotor. Is a rotor. Is a rotor, na? Yes. Is a rotor. So as it is, this is rotor, cylindrical rotor, right? Now the armature poles, wherever may be the armature poles. So for example, armature poles is here along the direct axis, north and south pole, along the quadrature axis also. Quadrature axis. What is the flux? Flux is from north to south, north to south. It is taking a path like this, north to south. So it is finding same area. Even north to south, if the flux is passing, everywhere it is finding same area. Everywhere same area means ammeter reading, voltmeter reading is constant. Ammeter, voltmeter reading is constant. No variation you will get. No variation. That is XD is equal to XQ. XD, XQ both are equal. See what is going to be happen when armature poles align with D axis, or Q axis, the air gap is same. The air gap is same. Reluctance is same. Same. Therefore, the ammeter and voltmeter reading, the ammeter reading is always constant. Therefore, the ammeter reading and voltmeter reading, ammeter and voltmeter readings are always constant, always constant. No variation of ammeter and voltmeter reading. No variation of ammeter and voltmeter readings. Because air gap is same. So that voltmeter by that ammeter reading is itself XD and XQ. Therefore, I can say XD is equal to, XD is equal to, and XQ is equal to that voltmeter reading divided by ammeter reading. Both are equal. Both are same. You cannot get any variation. You will get voltmeter ammeter reading is constant. That is XD, that is itself XQ. Right? So that's the reason it is not necessary to conduct slip test on cylindrical rotor synchronous machines. Both are equal, XD, XQ same. You will get some reading. Even though if you maintain the slip, we are maintaining all the slip, fine. But wherever armature poles are false, the direct axis or quadrature axis or any other position also, 45 degrees or 30 degrees also, it find always the same area. Therefore, there will be no variation of ammeter and voltmeter reading. Fine? Yeah, they are constant. This is about the slip test. Okay? Yeah. And in the next class, we are going to see the power flow equation. Power equation for cylindrical machine and power equation for salient pole synchronous machine. Reluctance power. Okay, and problems on that. Another type of problems on power flow equation. That will be the fourth type of problems we are going to see in the next class tomorrow. Okay. And any doubts are there, please you can ask. So we will discuss. So with this today class is 9 right now the time. So I will take 5:30 to 9. After that, doubts class. Sometimes it may exceed the time, maybe some 5-10 minutes. Okay. Yeah. I am unmuting you people.
Good evening, sir.
Good evening. Hello.
One doubt is that when we supply that field current, in that case, if NR is greater than NS, then power will flow from DC to AC side. Power will be flow from DC to AC side. Means let's suppose driven by some motor or motor.
Yeah. Okay.
Then power will flow.
Like here, if you are rotating at more than synchronous speed, it acts like a generator. Whatever you are saying, that's not
power flow from DC side to AC side. No?
Yeah, that is okay. Which component of the current? How much in this during this? How much DC motor power supply you are giving? Prime over input. How much? Even less than also okay. Are we connected any load on this machine? We are not connected. Just like up to some extent, you can treat it like a synchronous motor because I am giving the supply. Are we connecting? Is it load or no load test?
It is no load test.
No load test. No load test means what is if losses are neglected? What is active component?
Active component will be 0.
0. Only reactive component it is taking. IMU. That's what. Okay. And even if you rotate more than synchronous speed means how much power is enough? Small power is enough to rotate it more than because there is no active component, there is no electromagnetic torque opposition. Actually, if loaded conditions say there may be choice of electromagnetic torque opposition.
Okay.
It is very less. Active power flow we are neglecting. Active power flow. Anyhow, it is acting like a. You mean to say when rotate more than synchronous speed, it is acting like an induction generator. Okay.
Sir, but in the starting, if it will be motor means the system will start, then there should be reluctance power. Na?
That we will discuss. Reluctance power will be there here.
Definitely, na? That reluctance power will be the active component. Na?
Yeah.
Then how we can say this is no load case?
See how much reluctance power is equal to what? V square by 2 1 by x cube minus 1 by x3 sine to delta.
Yes.
But what is V we are giving? 1/4 almost or 20%. That reluctance power during this test also less. Otherwise, you give that is also one reason why we are giving very less means if you give rated voltage, reluctance torque will be more. Reluctance torque is more means opposition will be more.
Yes.
But during this, we are applying some 20%. 20% means V 20%. Reluctance power will be less.
Sir, can we hear?
And at the same time, we didn't come across that reluctance power. That's the reason I don't want to discuss here that reluctance power. Again, that is a separate discussion.
Yes, sir. But as a reluctance is changing, that reluctance power also changing, na?
Definitely, reluctance power will comes into picture. That I am going to discuss later because we are not aware about reluctance power. Na?
Okay.
Being the students, of course, already you might have seen that reluctance power. Okay. But now I am not introducing that reluctance power. That to be, V will be 1/4. How much it is? 25%. 20%, 1/4. And that to be, what is the reluctance power? V square by 2.
Yes.
V square by 2, 1 by x cube minus 1 by x sine to delta. 1/4 means what is that? 1 by 16 it will come. 1 by 16th means very, very less. Reluctance power effect will be less.
Means according to del, the power is changing.
Yeah. Those things we are not considering here.
Means okay, very less.
That will be there. That will be there. That is very less. And here I don't want to introduce that reluctance concept. Otherwise, the students will get confused. That will go aside. That is my intention. And that to be even practically also, they will apply 1/4, 1/4 because if you apply rated voltage, reluctance torque is more. And then your DC motor torque is there, na? That required also to overcome that reluctance power. Reluctance for nearly some 20% it will be there. But we are applying 1/16, na 1 by reluctance for actually 20%. 20 divided by 16 means how much it becomes?
Very less.
Very less. That can be negligible.
Okay. Thank you, sir.
Yeah. Hello.
Yes, sir. Sir, here the voltage used is line to line voltage or phase voltage?
Which one? Where? Line to
Sir,
line.
in this, yes, sir.
Line only we are applying. Phase also you can take, it is divided by √3.
So, sir, this synchronous impedance is given per phase, right?
Always per impedance calculations, everything is per phase only. Even every graph will be drawn for per phase only.
Okay.
Here, line voltage, when you are calculating, say for example, examiner here, slip test results. Okay, voltmeter reading line to line is 400. Right?
Yes.
Star connected. Then what is the XD means? Then you have to take divided by √3 and current per phase. Anyhow, star connection is line current, phase current same. If it is
Okay.
phase values are given directly same. In the test, slip test results are V phase maximum is equal to this. V phase minimum is this. Current phase directly given, you can take XD is equal to, no conversions are required.
Okay. Sir, in the case one, why is the drop in variac minimum?
Yeah. Drop means current is minimum, na? Current. IA current drawn is minimum. Direct as current drawn minimum.
Okay.
And that to be what will happen, in your lab, you can find large variation in the current, small variation in voltage. Voltmeter reading almost you can treat as a constant.
Okay.
That's the reason V by F I am saying constant very beginning, but later what I am saying varies V. But the variation in voltmeter reading is negligible. Why voltmeter variation takes place? Because of drop of voltage in the varia. Impedance is there, impedance constant we kept, but current is coming. That's some 5-10 volts. Voltmeter reading you can find variation is only 5-10 volts only. Current variation is more.
Okay. So in case one, the drop in variac is minimum, but does it affect the reading or how is it?
Which reading?
Sir, the voltage reading right now, you said it will be only varying from 5 to 10%.
Yes. That much only.
Okay.
Minimum, that is only minimum. For example, 100 volts you kept, say for example, right? It may be 95 or 105. That much only variation. In the laboratory, you can see the readings.
Okay.
Variation is, for example, it is 90 volts, say, it may be some 100 volts. That much only variation.
Yes, sir. Got it, sir.
You drop only, not much variation. That's the reason I am taking voltmeter reading almost constant.
Okay, sir.
I told voltage constant, but later during experiment, that voltage also slight variation. Why? Because current is varying, then drop is varying.
Yes, sir. Got it, sir.
Yes. Okay. Next. Hello.
Hello, sir.
Hello. Tell me.
Sir, this variac is maintaining the V by F ratio constant.
Oh,
Okay. So
maintaining, but small variation will come. I told very beginning, I am not changing, but due to drop voltage variation, little variation will comes into picture. That can be taken almost as a constant.
okay. Then this ammeter and voltmeter, these are analog instruments.
Okay. Analog.
And sir, we are noting down the maximum and minimum values.
Yes. Maximum and minimum reading. Two readings.
Using those two readings, so we are calculating these XG and XT.
Exactly. Yes. Exactly.
Okay, sir, that's it.
Okay. Hello. Tell me.
Sir, in reasons part, sir, third one, could you explain it again, sir? Because I didn't get that part.
Third reason. Huh?
Yes, sir.
This is reason 1, reason 2, 3.
The third.
Okay.
Yes.
Tell me third one. During the
Yes,
slip test, a rated voltage, reduced voltage has to be applied. You have to apply a reduced voltage. 100 volts I am applying, right? Because what is the current? Tell me. IA is equal to V minus E by ZS. Or generator E minus V by ZS. But what is E? This E proportional to flux, no?
Yes.
But are you giving any DC current? No. you are not giving any DC current, then how much it will be? Very less. There will be some armature flux cutting, some voltage may be there, but that is very, very less. Actually, our generated EMF in our alternator is mainly due to main field flux. But that main field flux we are not giving. Main field flux I am not giving. Therefore, no EMF opposition. V minus E. E that roughly 0 say. Then V by ZS. What will be the current? Very large. Current will be very large. Practical cases it is V. So for example, V is 400 volts. E 380 volts. 400 minus 380. 20 divided by ZS 1 ohm, say 20 amperes. Instead of that, V 400, this E is 0. 400 by 1 is equal to 400 amperes. Okay?
Yes, sir. Got it, sir.
Okay, right. Next. Yeah. Hello?
Hello, sir.
Tell me.
Sir, ఒకసారి 16 slide చూపియ్యాలి సార్. Screenshot తీసుకోండి.
Tell me.
Slide number 1 also, sir.
This is okay. You have taken a screenshot.
Okay, sir.
Okay. One, slide number 1. Right. This one? Okay.
Okay, thank you, sir.
Okay. Right. Next. Hello.
Hello, sir.
Hello.
Hello.
Hello. Chap.
Hello. Yes, sir.
Yeah. Tell me.
Sir, wonder that you said a point that FAD, that is direct axis MMF, and FAQ always find maximum reluctance irrespective of power factor.
Where? Yeah. Yes.
That is excellent.
Yes.
Okay. But in the previous class, we see that at unity power factor, we are getting maximum that will be the cross magnetizing effect.
That is okay. That is fine. I am not talking about that. When this power factor changes, what we are feeling here, FAD, is it finding same area?
FAD, no.
For this is another, you take power factor, this is the power factor angle, say IA. Then its air gap is different. If you are taking here 1 XA, you have to take armature reaction. For example, if you take here, XA will be different. If you take here, XA will be different. Here, if you take XA will be different.
Yes.
Because air gap changing, na? Like that, how many for 1 degree, every degree you have to take that many reactances. Is it possible to take?
No.
Not possible. That's the reason for simplifying, Blundell, he has given a solution. Instead of taking so many things, it is divided into 2 components. One direct axis, quadrature axis. Along direct axis, always air gap is minimum, quadrature axis maximum. Any power factor you can divide the FD component and the FA component, they will find the same reluctances, any power factor.
Then, sir, what about that current, ID and IQ?
That may be changes that we are not worrying about.
Then, can it
reactance is constant, or are you changing every time? As power factor changes, for example, in the data, XA is equal to 10 ohms is given. 0.8 lagging, 10 ohms, 0.6 lagging, is it 5 ohms? Not like that. Constant it is. Reactance is a constant.
Then can we say that it is the approximate of XT and XQ?
Approximate?
He is divided into two reactants.
Yes, reactance also we are dividing, one along the direct axis, another quadrature axis.
Okay. Means it is the each angle we are different reluctances.
That's what, each angle different reluctances. Can you take that many reactances?
No. So can we say that it is approximate? Means he taken ST.
Yeah. Not only instead of taking thousands of reactances, we are taking 2 reactances. FD, FQ. But any power factor, you draw FD component, FU component, forget about the magnitude of FD, FQ component. But the FD will always find same reluctance, na? Minimum only it will find.
Okay, sir. Can we find that reluctance in term of angle, some research paper or in some? Can we get some that is from angle to angle? It is how it is varying.
Yeah, it varies definitely.
Okay.
It will vary, but practically, is it possible to take so many? For example, 0 to 90 degrees itself, you can define 90 reactances. Is it possible?
No.
No.
It is infinite actually, means infinite number of reluctance.
Finite means it is for analysis purpose. If you take 2, air gap is FEAD will find always same air gap means the reactance is same.
Then we can't say that IDXT is not always greater than IQXT.
That we cannot show. Yeah. I don't know. Don't think ID always greater than IQ. It may be anything.
Because one teacher said that IDXT is always nearly greater.
It is depends on the psi value. Psi value.
Okay.
It is equal to IA sin psi A cos psi. It is there is no rule. ID is greater than IQ. No. XCAD will be greater than XQ.
Then
ID
phasor
will
will
be
be
lesser.
wrong, na?
Yes.
Otherwise, phasor diagram.
Yes.
Okay. Thank you.
ID, IQ, there is no particular relation. There
Okay.
may be less for some particular power factor. ID may be more, or ID may be less also.
Okay. Thank you. Thank you, sir.
Okay. Hello. Next. Hello. 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 I'm unmuting.
Sir, good evening.
Hello, sir.
Good evening. Tell me.
సార్ డెరివేషన్ ఒకసారి స్క్రీన్ షాట్ తీసుకుంటాను.
Derivation.
స్లైడ్ నెంబర్ ఫేజర్ డయాగ్రామ్ ఆఫ్ సైలెంట్ ఫర్ ఆల్టర్నేట్. నెక్స్ట్ స్లైడ్. వన్ మినిట్ సార్.
Okay, please.
నెక్స్ట్ స్లైడ్ సార్.
Ah,
ఓకే, థ్యాంక్ యూ సార్.
okay, right. So I hope it is clear. I am closing the session. Yeah. Closing the session, we will meet. Bye.